Right. Welcome everyone to our Enova webinar series. Today we're going to be talking about sustainable systems utilizing thermal batteries. Our agenda today is what's new from Enova, uh, presented by Andrew and Chris. Then we're going to pass it off to Stephen Scott for, to take us through the thermal energy batteries. And then at the end, we're going to have a little bit of a wrap up and Q&A session as well. Just remember, we're going to try to keep this informal. So if you have questions, please just unmute yourself and ask the questions as we go along.
We also have the chat or raise a hand feature or whatnot as well.
All right. Yeah, so just a friendly reminder that Andrew and I are always here to support our customers. We are your single point of contact for all energy related queries, uh, energy efficiency assists, whatever it may be. Uh, yeah, we offer a whole bunch of different uh, solutions. We can look at your bills, we can analyze your bills, we can look at your power consumption and everything else. We can help you make informed decisions and seize opportunities to enhance your competitiveness. And we can also offer you regular reports on energy efficiency and how how you're utilizing your power. Just remember, we're just a phone call or an email away. So what's new from Enova? So supporting our customers. So a few weeks ago, I received a call from a customer who was noticing frequent power blips. So I checked with our control room to see what was going on. It turns out there were a few incidents caused by animals coming in contact with the wires. To fix this, we reached out to our operations team to get some animal guards installed, which should help keep things running smoothly and avoid any more interruptions. It's just one example of how we're helping our customers. We've also done multiple energy efficiency assessments for small commercial offices. Uh, just and over to you, Andrew.
Yeah, right on, Chris. Things I've been up to is done some power factor analysis. So I actually had a customer that was investigating solar panels on the roof and did some billing analysis and realized that their power factor was incredibly low. Asking me for my assistance, do I need to do this? Dug into their hourly data, and I can actually pinpoint the hour of the day that their power factor equipment stopped working. So they're like, "Do we need power factor equipment?" And I'm like, based on this, it looks like you had power factor working fine up until this minute or hour that it stopped working. So then, they moved a couple panels of sheet metal, and oh, there it is. Our power factor correction is right there, and it wasn't working anymore. So they had to replace it, but that analysis that way we can help them to decide what kind of kVAR they need to add and if it makes sense. Typically power factor has to be rather low, sub 80 to really make a good business case out of it. But that's just something that we that will help with. Then also I had another customer that purchased a new building in our property or in our territory, sorry, and was wondering why their bills were so high. They said they didn't have any equipment in there whatsoever. So then I had a meeting with them, talked to the, the manager that was taking care of the building, and he went around and started shutting off loads. And then we revisited their hourly data the next day, and we could see the direct impact of all that energy conservation, turning things off, had the effect on their bill, and they were able to see that the following invoice. So um, prior to that, it was more or less, why are you guys charging us so much money? A little bit of education. Now they realize, okay, this is what the real um, issue is.
And so
Back to you, Chris.
here's a little story about empowering our community. Through July and August, we had an e-billing campaign where we donated $4 for everybody that signed up for e-billing to the Humane Society of Kitchener-Waterloo and Stratford Perth, and we raised $5,000 for that. Nova employees also raised $3,000 through Heart and Stroke Foundation through our charity committee summer campaign. And we are currently just at the tail end of our Enova Department Food Bank of Waterloo Region Drive. I can't give you any results right now, but it's looking pretty good for everyone. And then
Yeah,
now we're going to talk about learning together, and we're going to pass it off to Andrew.
right. So, like I said, we want to learn together, as things are progressing, the MD atmosphere or the environment is changing uh, quite drastically. We want to be able to take you guys along with us and find topics that make sense, so that we can learn about and we can share with you. Uh, Bring people in like Stephen today to discuss outside the box concepts and whatnot. Or if there's specific things that are actually interesting to you that you really want to know about, and there might be a larger following that wants to as well. We need to hear that from you. So I'm going to try to start a poll here, if you don't mind, real quick. Uh, so we have to poll. Okay, so if you could take a quick moment here to fill out that webinar topics poll. It should be on your screen. It'd be absolutely great if we can get some ideas from you. I know a lot of these are kind of general concepts, but uh, take it for what it's worth, I guess.
Yeah, and it's going to help us guide our webinar series moving forward as well.
Mhm.
So any input is greatly appreciated.
Okay, so we'll let that poll go on for a little bit longer here. I'll end it. In the meantime, let's send it over to you, Stephen. Thanks for coming today.
Awesome. Thank you. I'll just introduce myself. So I'm Stephen Scott, Steve or Stephen, whatever. Sustainable systems leader from Terrain for Canada. Originally started with the company in 1997. So sales role, been sales leader on the operations side, and as a company with just getting renewed focus on decarbonizations and electrification of heat, and created these roles across North America. Just to give you a background. And as I go into it, like some of the reasons why, there's everybody on an electrification, heat, and decarbonization journey. Some people don't know where to start. Some people are like work for companies and have goals that are very specific and explicit. So I'm just going to try to cover everything in general. If you can go to the next slide, I'll just go into the
Okay.
perfect. Then next slide. So just an agenda, I'll quickly go through and define decarbonization just so that we're all on the same page of what we're talking about. Talk a little bit about renewable energy and how thermal batteries integrate with that and can enable renewable energy. Then I'm going to get into something new, electrification of heat, and then tie in current electricity rates and incentives. So this is where you say that, well, you really need to be talking to Andrew and Chris with all of this. So then there's just a back and forth. And especially when it comes to decarbonization, it's going to require a lot of teamwork and a lot of collaboration. So on to the next slide. So the one thing that's common for us, at least, I'll start there, is a goal of governments to be net zero by 2050. And really where there's reports in Canada's target was to have be 40 to 45% below 2005 levels by 2030. The not so good news, but they published a report in May, earlier May of this year. We're only 7.1% below the 2005 baseline. Listened to Environment Canada yesterday speak that sure the emissions intensity have gone down, but buildings on our side of it, the emissions have gone up. So there's going to be, no matter what happens with governments and even into provincial levels, there's going to be extra work needed to meet the targets. Into some definitions on the next slide. So, decarbonization, what is it? A simple word or simple explanation is the process of reducing or eliminating carbon emissions. And on to the next slide of where they break down within our industry. Globally, from the emissions, 40% of emissions are generated by the built environment. So when it comes down to what impact our industry have, like building owners, utilities, it is very big and very significant within the global warming to be able to address climate change and CO2 emissions. For the next slide, when we break it down in our business, we have what we call three scopes or three categories. And the first one are scope one emissions, really what's on site. And if you think that, say, you're burning natural gas for heating the building, doing domestic water heat, well, that's a scope one emission. Or it could be refrigerant emissions if you have a chiller and say that it's leaky, because that has global warming potential. It gets up in the atmosphere. So that's what you're directly emitting into the atmosphere. And some of the solutions to that, refrigerant management, not talking about today, but like going to low GWP refrigerants and addressing that. Electrification of heat on site. Not going to be talking about that, but that's another topic that you can as well. Then there's scope two emissions, and this is where utilities become really involved. So scope two emissions, if you're heating and cooling your building with electricity, well, the scope two is, well, what are the emissions from the utilities that are being provided to your building? And yes, there's been power agreements where owners have gone out and purchased green electricity as well. Owners and building operators can impact this by taking energy efficiency measures, so that you can simply putting in energy efficient equipment. You having on-site renewable energy, and I'll describe that a little bit more, or going to something that may be more involved, such as addressing the building envelope to increase energy efficiency. So all of these things will happen. There's a third one that we call scope three emissions, which are everything else. So then to give a couple of definitions on there, embodied carbon would be the cement that goes into making the foundations of the building, the steel that goes into the rebar, then the heating and air conditioning equipment that is manufactured, that gets transported to site, all the natural resources that go into building that built environment. So when we get scope one and two down to zero, embodied carbon, when we get closer to 2050, becomes a bigger and bigger impact. And just this past Monday, Train's owned by Train Technologies, and we committed to, for our products, a 40% reduction in the embodied carbon of what we're building by 2030. So we just made a big announcement there. But all of these coming together are called carbon footprint, and decarbonization is making that smaller. And then there's the other side of it. It's when we talk about decarbonization and the how, it's complex, it's crowded, it's fragmented all over the place. This week when I was in Vancouver, drive by the airport, they've committed to 2030 net zero. So they're farther ahead, and some haven't started, which is everybody's just different and on their own journey. But just part of this is just educating the community, and it's not. And if you're feeling overwhelmed and maybe you're on an island somewhere and you don't know where to start, well, this is pretty common across all of North America and globally. It's really similar. On the next slide as well, where on top of that, we have other goals where companies will have environmental goals, and investors like BlackRock will be demanding from publicly traded companies that they have to have specific targets of how they're going to meet, say, a 2050 net zero goal, and have that documented out, or they're not going to get investment money in their business as publicly traded companies. So it certainly starts to add up. If you go on to the next graphic, should pop up. Yes. So majority of provinces have adopted targets. We know that there's always politics involved. There's the axe the tax on the bottom right-hand corner, so we never know what will happen politically. But generally, the goal of getting net zero 2015 is still going to be there, but the pathway just may be different and take twists and turns as we move along. The next slide that we have is just breaking it up into decarbonizing HVAC systems and breaking it down just one final level. of where we look at on the right-hand side, scope one emissions, electrification of heat, of where we can really look to transition from burning fossil fuels on buildings and electrify it. Also, refrigerant management, that's a separate topic as well. On the left side, always working on energy efficiency to help improve that. And I'll be going down in a little bit more discussion on renewable energy and also the electrification of heating, but not minimizing any of these. They're all going to be needed and all going to need to partner with utilities and partner with so many people in the industry. Now, transitioning into renewable energy. In the next slide. So in the past, if you click on it once again, you have stored energy. Well, what we know how we've managed the electricity grid in the past. Coal, oil, natural gas, fossil fuels, they have a high amount of stored energy. If on demand we need more energy to the grid, we burn more. Well, the difference is with green energy, with solar and wind, well, we can't just flick a switch and get more sunshine and get more wind. We're at the mercy of whenever it happens. So we have to figure out where is the storage for these technologies. I'll just give one story. Other utilities have gone different ways. If we could, it would be nice to take a trip to Hawaii, but we're not. Just imagine that you're going to Hawaii, and what they did is since they have a lot of sun, they went down the route putting solar panels everywhere. Well, now they got to the point where if you want to be connected to the grid and have solar panels, you have to get a permit to have solar panels plus on-site electrical storage. And the reason being is that they had so much green electricity during the day, they couldn't use it, and it made the power grid unstable. So then what happened? So then what do they do when when the sun goes down? Well, Hawaii's an island. They have to import diesel, and they run diesel generators overnight. So this is where, when we start to think of storage, and we're talking about energy storage, we really need to be talking to your electrical utility providers, because it's a different conversation depending on where it is and different drivers and different dynamics. So that when we do talk about, especially specifically thermal batteries, well, how can that impact the grid? And that can be very local at times. So then that's like, reach out to Andrew, reach out to Chris, and have those discussions whenever you're looking at whatever measure that you're taking, because it can have a big impact. And it could have a big financial impact as well. Now so where's the storage? I'll get on to the next slide. So energy storage technologies of what's out there today. There are many different types of energy storage will be needed. They're being implemented today in Ontario on what we call both sides of the electrical meter. So we have on the grid side, we have pumped hydro, there's compressed air, there's flywheels, there's batteries, where you think of large battery stores, chemical batteries, and then there's on the building side of the electrical meter. So at the building itself, so batteries as well, talked about those, thermal mass. And the one that I'll talk about is thermal batteries. They can call it something old and like something new again. But what are the thermal batteries? We'll go to the next slide. So train thermal batteries, we purchased Calmac about seven years ago. I've been in the business of making them about 40 plus years now. It's a tank of water filled with water with about 5 kilometers of plastic tubing, and they put glycol in the plastic tubing, and you freeze ice when rates make sense, and then you melt ice when rates make sense. So just like the one tank has enough capacity to cool approximately six homes, depending on the temperature. And on the next slide of the system, when we think about 3 components, ice tanks, been around 40 years. Chillers to make glycol, cool glycol. Chillers have been around for 100 plus years. and the controls to be able to integrate and make the controls decision. So it's really the four components or three components, pardon me, that are there, really charging and discharging of when it makes sense for the system. Graphically, if the next one is where it's traditional, and I'll just say traditionally being used as an example. I brought up Hawaii as an example because then sometimes things can change, and that's why you need to be talking to the utilities. But in this, just in this one example, air conditioning on say a commercial office building can account to 40% of the summer peak daytime load. So what's been traditionally done is, well, you make the ice overnight when rates have been low, and then you melt the ice during the day when rates are higher. So then that helps reduce the peak electricity grid and enable, so it flattens out the utility profile and makes it a lot easier for the utilities to integrate green energy into the grid. So then you don't have to put in peaker plants, reduce the transmission lines, and then also on the bottom here, support advanced grid services and demand response. In the past, a lot of demand response have been utilities going to large industrial users and telling them, hey, for this period of time at peak energy usage, we want you to shut down your production. Well, this with thermal batteries, production would be cooling, whatever it may be. It could be industrial, it could just be comfort cooling. Well, you shut it down and you still have cooling so that you're not negatively impacting your business. The next slide is really two ways of doing it. And on the left is partial storage. So roughly you'd use, if you think of, say, 100 tons or 100 kilowatts of energy, the partial would be chiller takes up 60% of it, 40% is roughly ice storage. So then what it does is reduces the size of the chiller that you would normally install in the building and reduce the electrical size, or you reduce the amount of electrical needed in your chiller plant and you free up electricity for other things. Those other things could be electric vehicles. It could be whatever you may want to use it for. You could replace a gas heating boiler with a heat pump to make domestic water. It could be whatever you want. But it's really the costs are similar to the first cost without incentives of a traditional chiller plant. But when we start to, when I get to the end, when there's the rebates within the system, when there's utility costs, it can certainly be a positive, financially positive as a driver. The other one that we looked at as well, again, depending on utility and rate structure and your business, is full storage. This requires more cost because then you're not downsizing the chiller, you're keeping it at the same size, but then you're taking your purple hours on the right to be sized for full storage. Well, this can be more advantageous for customers who have high time of use rates, maybe impacted by the global adjustment charge, or maybe discussing things with the local utility of how they can enable demand response. So this doesn't necessarily have to be a full-size chiller plant of taking everything offline, but it could be taking a portion of the system offline as a demand response. So it could be something like partial storage, or it could be to the extreme as full storage as well. The next slide just gives an example of, well, how can we retrofit existing plants? So I just put this one as a large plant. So then really heat exchanger, it's been done before, integrating it into the system. So the things on the right with the ice tanks and the ice making machine, well, that would be the glycol. And if you had an existing system that was chilled water, you keep the chilled water as well, so that you don't have to retrofit the whole system. So just saying that it can be done and it can be retrofitted into systems. To quickly summarize, thermal batteries provides the demand flexibility and can reduce the reliance on the grid, thus your costs as well. That's historically has been the driver to reduce the cost. The next one enables renewable energy and decarbonization. So when you're flattening out the electrical profile, the utilities really like this because then they can it can take advantage of the energy usage at other times of the day. And again, that's where the conversation with your local utilities will help out of well, when does that make sense to use them? The next point. Assure reliable heating and cooling with redundancy. You get additional flexibility for it as well. And then the last bullet point, incentivized by utility programs and potential tax incentives with local funding. The one frequently asked question that we get on partialized storage that I've been asked before, well, what's the round trip energy efficiency of going from thermal batteries and then the cooling? When you're doing it overnight, in our climate, it's generally equal from a BTU perspective. If you were going to, say, Nevada and the desert where you don't get the temperature relief overnight, then it's a little bit more energy. But they're more worried about saving water and getting away from cooling towers and restricted utility grids for other motivators. So that there's the ice storage can certainly address multiple motivators, but it's really looking at how to enable green energy and renewables within the grid. Then I'll go to something new on electrification of heat. Then the next slide, just as a summary, just for awareness, there's a lot of different solutions that are out there. Ground source heat pumps and geothermal. That's definitely one solution when it comes to electrification. VRF is another one. Packaged rooftop equipment, dual fuel, hybrid systems, they're out there as well. Chiller heaters, heat recovery, getting into more development on higher temperature heat pumps, that's out there as well. One new thing to introduce you to is using storage source heat pumps. And rather than using ice to cool, well, what if we do the reverse and use ice to heat? Next slide is the challenges that we have when we look at air source heat pumps. Well, you have a couple of options that you can do here. Traditionally, you can just take those gas boilers and you can replace them with electric heat. Well, that's going to cause a problem because the coefficient of performance is 1 kilowatt in, 1 kilowatt of electric of heating out with electricity. That requires a lot of increase in electrical feeds on buildings, which is just going to make peaking even that more difficult. When you get into urban environments, well, it gets a little bit more difficult to drill underneath the ground. When you get into mines, if you try to go very deep, well, the temperature flatlines at around 40 degrees Celsius if you go a few kilometers deep into the deep bedrock. So then it starts to get hard to do geothermal. Well, what if we take on the roof and we put air source heat pumps on the roofs of buildings? Well, they're limited as well. And you're probably going to need a lot of space to be able to provide all that heating and displace the heating. So then go to the next one, next slide. Well, what about using thermal batteries? So this is what they did in Manhattan. They used tanks, and just to give a little bit more information on the tanks, so 7.5 feet wide, 8.5 feet tall. Each tank, when you change the phase, when you either melt or freeze ice, that's about 2 million BTUs of energy, or about 160 ton hours. So a lot of energy is stored in this water, and 3 of them will take up 1 standard parking spot. So then they don't take up a huge amount of space, but then when money incentivizes that, then that can certainly be a game changer. Or if companies have decarbonization targets, that can help move things along as well. So how does this work as a storage source on the next slide? Well, now what we're looking at doing is something new and innovate to make an all-electric heat pump even possible in cold climates. So with this diagram, when we say it's energy efficient, one, we're keeping heat within the building, reclaiming heat within the building. So melt some of the ice to create the water. And then when heating is needed, freeze the ice and then use a chiller heater to pump that energy as heat into the building. The difference is, and when we're talking about cold climates around Ontario, we'll get to easily in the middle of winter, minus 20 degrees Celsius. Absolutely. And the efficiency is that the chiller heaters are taking the energy from the thermal storage batteries at, say, 0 degrees Celsius, which is a lot less work and much more efficient than if it had to do solely by an air source heat pump. What it also does is it also enables the chiller heaters to operate at higher temperatures versus traditional heat pumps. You also get an energy benefit in this case because since you're heating with ice rather than at the lower temperatures, you do save energy on the building. The next slide gives a little bit of a graphic heating design day, and say you had to size it for your heating design day of 12 million BTUs per hour. But if you move forward, if you just solely do it air source heat pumps, in this example, you need about 10 of them on the roof. You just hit click once to go forward. There we go. Maybe more to accommodate defrost depending on your building type. When we source from ice, what we end up doing is when you click on it again, we then set it based on the average use over the day. So when the building, generally at morning warm up, needs the most amount of heat, we source it from the ice tanks. And then during the rest of the day, and not for every building, but you need a building that has an area that would need some cooling. So then you cool it with ice. So then you shift the BTUs within the building during the rest of the day. So when you click on the next one, so then you're moving them from other times of the day, the BTUs, to be able to shift them into the building and keep those BTUs in the building by using ice and using the batteries as your source. So then on the next one, you end up on the roof, cutting them down to 5. So for urban environments, using thermal batteries can just another option of what we're working on when you're heating to be able to electrify buildings with a different option. Now, the next slide will show a graphic of what happens. So what we show right here is this is your air source heat pump of what we experience today. As the outdoor temperature gets colder and colder, capacity runs off. And as you get to 0 degrees Fahrenheit, it can only, the vast majority of them can only produce hot water at roughly 90 degrees Fahrenheit, which in general isn't hot enough to heat buildings. Even when you look at, say you retrofit a building for condensing boilers, you need them to be around 130, 140 degrees Fahrenheit to get those efficiencies. When we have the air source heat pump sourcing from the thermal batteries, that fixes it at 0 degrees Celsius or 32 degrees Fahrenheit. So when you press the next slide to go forward, it then flatlines and extends the performance curve of a traditional heat pump of what we have today to extend it to say 130 degrees Fahrenheit and down to ambience as low as minus 30, minus 35 degrees Fahrenheit. So you're taking equipment that we have today, technology that we have available today, and expanding that operating map and getting it to operate at a more efficient area as well. What does the system look like? Well, we also do add a trickle heater in here as backup. This is what we look at from a technology just to make sure that there may be that coldest day where you need a little bit of extra heat to melt the ice tanks. So what's new is this arrangement is new, but the ice tanks, we've been making them for 40 years. Heat pumps, we've been making them in Europe for 30 years, in North America for 20 years, chiller heaters and heat recovery, we've been doing it for decades. But it's just more of the controls and the optimization of all of this that is new. What we target is for the storage source is climate zones 5 and colder. Reason being is that, well, if you go to, say, California, where their design temperature is like 2 degrees Celsius during the winter, well, then you're more efficient to use air source heat pumps rather than thermal batteries that are colder. We do have on the next slide, we do have a tool that we can use to estimate the amount of CO2 energy savings. I'm trying to make this not terribly political. Using examples of the US markets of a dirty grid and a clean grid, don't want to pull out our own market. So we do have a tool of estimating, and we take two of the exact same buildings, one in Chicago, one in Buffalo. So Chicago has a relatively dirty electrical grid. Buffalo, closer to Ontario. If you're just burning natural gas heat, like we would today, say 80% efficient, they both burn the same amount. If you went the next column over where it says electrical heat, if you converted that to heating electric boilers with a COP of 1 based on the utility grid emissions, that is in the CO2 equivalent, it would go up higher, much higher significantly on a dirty grid. On a cleaner grid, let's say Buffalo, yes, your CO2 equivalent emissions would go down. When we convert that and look at storage source heat pump, when we're operating it more efficiently with higher coefficients of performance sourcing from the ice tanks, we then get that energy efficiency increase. So, or CO2 emissions decrease. And with even on a dirty grid, it makes sense. And also on a relatively clean grid of Buffalo, we certainly can reduce the CO2 equivalent emissions. Again, it all depends on what your targets are, whether it be your company's targets are, your building's targets are. If it is a CO2 emissions target, then this is just a different way of looking at it. Next slide, thank you. So where have we installed this? So far, we've done one where we're testing this out. We figured we would do our own building. And if something goes wrong, then it impacts our own employees. And we have our training and learning center in La Crosse, Wisconsin. We installed it in November of last year. It's an 80,000 square foot building, has 180-ton air-to-water heat pump, 210-ton chiller heaters, 7 ice tanks, and we're using as a research project to optimize control, address heat recovery, figure out what's the best sequence when we look at airside economizers and how to operate it. Last winter, we didn't have as cold of a winter that we wanted, crossing fingers for a cold winter this year to be able to try out the technology. And we're absolutely looking for people who would be like beta sites to look at an installation, so that if they are interested in that, then certainly more than happy to have a conversation. Next slide, I'll transition to electricity rates and incentives, and just like with all these technologies, it can sway decisions all over the place of what where you're looking at. So in this slide, I took the US data, and for Canada, I converted it to CO2 pounds of CO2 equivalent, so that we have the same yardstick. When you look at the US data at the lower graph, this is where data can be, I'll give you 2 examples, can be very misleading. The second one on the US of 1575, that's HIOA. So that's one of the Hawaiian grids. You see that that's very dirty, but that's because they're bringing in diesel all the time to burn diesel overnight. However, during the day, they have a lot of solar. So that this is where my shout out is that you need to go to your local utility, and in this case, Enova, have a conversation of them, whatever measure that you're looking at. Well, what makes sense if my business is looking to reduce CO2 emissions and I have a target to do, especially with scope 2 emissions, reach out to your local utility. You look at Canada, here's another example, PEI 8.8. I went, well, like, wow, that surprised me. Dug into the data, looked at their utility grid, and yes, they have a lot of wind and solar. They have peaker plants during the summer, like small peaker plants of diesel to take off the peak, but they also have two underwater lines that are connected to New Brunswick, where they import a lot of their power from. So indirectly, they could help impact New Brunswick's grid. So again, that just goes to show that you need to have that conversation with your utility provider of what makes sense, because every grid in every area can be different, and even down to municipalities and to various various postal codes, there may be differences there as well, because it could be a transmission issue that they're working through. And on
Yeah,
to the
Steve,
next.
actually, I'll just chime in there real quick. And what I've found
Yeah.
is it really depends on the time of day as well, right? So you might have this as
Yep.
a kind of an annual average that might factor in. It's a quick calculation, but what we've done for some customers is we've actually gone hour by hour using some data by the atmospheric fund to find out what your hourly emissions are, and then sum that up, and you'll actually see quite a different number and impact, I guess, of the decisions you're making based on the hourly data.
Yeah, and I've even seen, and Andrew, I've seen graphs where they have heat maps for like the 8760 every hour for a whole year of where it changes, where it can be dirtier or cleaner by the hour. And that's where you need to have the conversation, like where Andrew and Chris are the experts. So then you get them involved for that. And then so the next slide is just going again, just to bring up as a topic, sometimes the rate structures can change your behaviors as well. So it could be CO2, could be dollars. So depending on where you are from your rate structure, you could be Class A dealing with the 5 peaks and trying to manage your 5 peaks from a financial perspective. Well, hey, how could thermal batteries help this? Could be something with CO2, or it could be with dollars. Class B as well, because you find out at the end of each month. So then that's just where the conversations can go, depending on what your drivers are, whether it's financial or CO2 equivalent or both, and you're trying to balance things out. The next slide, like this one as well, especially on small commercial and residential and these ultra low rates. What these differences in rates, they're giving a market signal. Like, so this is more of the stick, you could say, where it's there in the market, where whether it's a demand charge or where it's combined peak and very high peak, relatively high peak rates and relatively low peak rates overnight. This is a market signal. Plug in your electric vehicles or do your thermal batteries overnight, just as an example. But then this just goes down to the conversation of, hey, well, what makes sense for your business? What's your load profile? What's your cooling load, heating load profile? If you're doing small manufacturing, how does that work into it? So it all just comes down to collaboration and teamwork to be able to move this forward. Last 2 slides. First one, well, Save on Energy program. Yes, there's example. There's lighting controls, HVAC redesign, chiller replacement, variable speed drive installations, a lot of prescriptive. But then on the last one, with the last slide, I'll answer, well, where does thermal batteries come into play? Well, they're in the custom. Summer peak kilowatt reduction. So then there's going to be verification in there. You probably want to talk to Enbridge if you're reducing gas heat, because you can have additional incentives there. One key thing, speak to Andrew and Chris early on in the project. Don't wait until you've issued contracts on it. Then you'll have a problem and you won't get your rebates. But for peak kilowatt reduction on the custom, the $1,200 per kilowatt of demand savings is the most lucrative in North America right now. So that the dollars really pay on partial, like if you have a cooling building and you're reducing the peak load, they really do pay out.
Yeah,
Really incentivize.
Yeah, it took the custom track away because they didn't realize how effective it was, and when they brought it back, they made sure to dangle that carrot so that people could take advantage of it when it now that it's back. Um, and just to add on to that, when it comes to the custom track, we do have data loggers here still. We can connect it to any kind of a piece of equipment to monitor it over 2 weeks or a month or whatever the case may be. Get a nice little baseline profile there, and then whatever options you're considering, we can add, add that to the model and try to estimate what the energy savings was. So if you're trying to decide what kind of option to go with or what equipment to go with, we can help you with that analysis. And one last thing, just to comment on Stephen's note there about making sure that you get the incentive application in before you go ahead and purchase anything. Apply before you buy. That's kind of our slogan here. So if you take anything away today, make sure you remember that one.
And
Okay.
any questions?
Oh, we got one in the chat here. Can you please review and explain the collecting energy for climate zones 5 and colder slide schematic?
Sure. Yeah. What's that showing? Is it trying to cut the slides down as much as possible? What that does is that you can source. I think it's the previous slide. You can, yeah, or one more backwards. Yes, this one.
Okay.
So what this does, so the 7 a.m. Heating load. What this shows is that, say today, without storage source, if you have to size for your heating load, you size an air to water or air source heat pump based on what is that peak instantaneous heating load that you need for that day, plus an amount for defrost, because it's going to be like design day is minus something outside and much more below zero. So you have to size all of your air source heat pumps, outdoor heat pumps for that peak instantaneous. When we're sourcing from water, you end up taking the overall BTUs, is now we end up downsizing the outside, and then we put the heaters inside the building to take care of the actual BTUs. But then, rather than sourcing from the outdoor ambient, we are sourcing from those ice tanks and we are making ice. And then so the green arrow there is that when there's less heat, we're starting during the day, we're melting that ice. So there's a few different ways, and this is where we optimize, where we're working on optimizing the control algorithms. We could melt the ice, and if you go to the next slide, or and one more where it shows the system, the different ways of melting the ice during the day. So the ice tanks could be melted by the cooling coils, providing cooling to the building somewhere else in the building, like a core zone. It could be from the air to water heat pump, because it could be partial, like this time of year. This time of year, it's warm, or last week, it was warm during the day, or it was like cool during the morning where we need morning warm up. Then later on the day, it gets to 25, 26 degrees Celsius. And then we need cooling. Well, you could use the tanks to do that, or you could have the air to water heat pump do that, or in extreme cases, the trickle heater. So these are the type of algorithms that we're working through the live building to figure out, well, when does it make sense to do one or the other, or in between, from an energy perspective, to keep as many BTUs within the building.
All right. Thanks, Stephen. Thanks, Scott, for your question. Any other questions out there, guys? All right, you know what that means, Stephen. You did a great job. Thank you.
Really, thank you very much. I really appreciate the opportunity to be talking with all of you.
All right.
Well, like Andrew mentioned before, these are going to be posted on our website, and we'll be sending out a copy of the link and a copy of the PowerPoints to everyone later.
Yeah, and there was one additional question that just came in the chat. Where can the thermal tanks be installed? Are they limited to ground mount systems, or can they go in mechanical penthouses or on roofs? They can, I'll answer the first one. They can be installed really anywhere. They can be buried, but not buried and pave a driveway over top of them, and maybe like buried outside, and then put mulch and put planters on them, and just need some access to it. Can they go in mechanical penthouses on roofs? Well, if they can, not terribly frequent because of the roof loading. You're adding a lot of water and a lot of weight to the roofs if you're replacing a pool. But in many cases, if a pool can go on a roof, then so can the ice tanks as well because it's water. So there's lots of places where they can be located. Are there maximum minimum size limitations to the systems? Are they too? Really, it comes down to the size of the tank. That's really where the physical limitation comes into play. We started with an 80,000 square foot building for the storage source heat pumps for ice tanks. If it's just like ice only, then that's about, depending on your temperatures, roughly about 150, 160 ton hours as a smallest system. So then you're looking like 20, 30 peak tons of type of an installation.
All right. Just a comment here from Stephen Litt. Thank you for that. Maybe unmute yourself and just give us a little briefing of that comment that you made there.
Yeah, so all of our projects are, we work closely with CMHC to get some deep energy efficiency, generally no natural gas, all air source heat pumps. In the region, we struggle with ground loop, geothermal. I'm fascinated to see, and I guess we can take this offline, but I'll just see how we can better implement this as a hybrid system. The one challenge I'm concerned with is these systems get really, really complicated, and our maintenance people we almost spend as much in maintenance and as actually the energy saving. So anyway, we take it offline, but very exciting to see this. I've heard of one other project in Kitchener. I think it was One Young that was going to do effectively store water as a battery on the roof. I don't think Berneinheimer ended up doing that, but all good stuff. Appreciate your input, folks. Yeah.
Thanks. Great. Okay. If that's it, Chris, over to you to wrap us up.
All right. Well, thanks everyone for attending. We're right on schedule, and I wish you all a great day, and we'll see you at the next webinar. Thanks, everyone.
Thanks. Take care. Thanks, Stephen.
Thank you.
Thank you all.